Hey everyone, I hope that you're all doing well. In this lecture, I want to discuss with you some of the complications that arise when we actually move to doing inference in practice. This might seem like technicalities, but actually I think this material is quite interesting and it really gets to the heart of what it is that we're doing when we do inference. So we've been proceeding so far with three assumptions that we should now take a little bit more seriously. The two of them turn out to not be a big deal, and they can usually be ignored. One is a very big deal, and it can never be ignored, and it often leads to some kind of thorny problems. That thing is that the assumption that we actually have an SRS, or a simple random sample. That's a big deal. We almost never have one, and dealing with that can be something that's very simple or very difficult, and it just depends on the context. Our second assumption is that our variable is normally distributed, which is typically not a big deal because of the central limit theorem. And really, I'm just following this format because our book actually has been making that assumption. I have not. They make it for what I think are extremely poor reasons. So we'll just discuss that a little bit further in a moment. And then finally, the last assumption is that we somehow know sigma, but not mu. So we've been assuming that S is simply immediately equal to sigma. But then we haven't been making the same assumption for x bar and mu, and that, obviously if we were just making that assumption that x bar and mu are the same, we would have no inference problem to do. We would just say, well, the sample mean is the population mean. Why are we allowed to do that with S and sigma? It turns out that we're actually not really directly allowed to do that, and we'll deal with that problem more in the lecture that'll come after this one, but it's good to flag the problem now. So the first assumption is that we actually have an SRS, and it's a really important thing to verify. It's hard to get right, too, because non-random error, i.e. non-sampling error, is not fixed by our procedures. So a biased sample, for instance, comes from a different population than the one on which we hope to do inference. We can't do anything about that. So if you get a sample, say of people who are being polled about their choice of candidate in the upcoming election, and you happen to get people that respond to an online poll on a website that is like a blog that people who are super geeks about politics read, that information comes from that population, the people that read that blog. You cannot do anything once the sample is gathered to make that more representative. That's a really big deal because very many casual samples are biased in that fashion. In practice, even when we do have a sample that's gathered in a way that is meant to be representative, we have to account for what is known as complex survey design. The generic term for this is applying sample weights, but even then there are kinds of survey design that are much more complex than simply weighting certain observations more, and this gets really into the heavy machinery of like actual inferential statistics. I'd like for us to do some of this in this class, but we may not in fact get to that. This is a pretty important oversight of a lot of classes like this because there's just so much to discuss. But unfortunately, it's also something that you have to do in order to be able to produce any statistics that have like really any actual worth. So this is a little bit tricky. Hopefully we'll have time to get to it. Finally, the third fact is that measurement error is a big deal. So you can consider all of the issues discussed in our week on survey methods. And this really isn't so much about having a simple random sample or not, but it's about the absence of, like, a simple random sample only works if measurement is at least unbiased and hopefully not super noisy. And in fact, it's often biased and super noisy. So we can have wording effect problems, we can have recall problems, we can have social desirability response bias problems, we can have the fact that the researchers just effed up, or I shouldn't say that, that's a little dismissive, but like the use of bizarre brackets on income on the GSS, that's something that we can't really go back and easily fix. So you have to consider all of these things, and in this class we don't spend a lot of time dealing with these problems, but they're very important things to be apprised of. So what can we deal with in this class, and what are we going to spend a lot of time on? Well, one thing we've already learned to deal with, which is the assumption that our variable itself is normally distributed. This is totally disposable, and we've been ignoring this rule the whole time. That's actually the entire point of the central limit theorem. Means and counts are normally-ish distributed. I truly don't know why our book points this out in such a tortured way. It makes the central limit theorem seem pointless and like unconnected to what's around it. It makes it seem like statistics is restricted to a much more narrow domain than it is. It's a little bit like how the book doesn't explicitly point out that the binomial distribution is a sampling distribution and it's intimately related to what follows. I don't know. It's With all due respect to the authors, it's a book I loved. I read a much earlier version of it as a student when I first learned this stuff. I loved it. I thought it was great. As an instructor, I've come to think that it's severely flawed, and if I end up in a tenure track position, I will write my own book on this, just because I think most of the ones that exist have pretty severe problems in different ways. I don't mean any disrespect to our authors who know more about math than I do, but the way that they present things, I think, is, they know more about the truly technical details than I do. As far as like presenting it in a clear and logical way, I think it's deficient. So that's just a comment on our book. It's still really useful. You got to have a book. It has lots of really nice diagrams, but there's many things where they, I think, lose readers because they're just, they make things kind of like unnecessarily complicated. Hopefully when I introduce things that are complicated, it's usually stuff that they really should include because it makes stuff a lot easier. But yeah, there's no need to assume this. That's the takeaway. There is one caveat, though, which is that you should always be aware of the problem of outliers. We haven't really talked about that in a while, but we did define outliers before using the 2-key rule. It's observations that are larger than 1.5 times the IQR plus Q3, or the same mutatis mutandis for Q1. And we maybe haven't given that enough respect recently. So strong outliers or really severely non-normal population distributions can cause problems. But severely non-normal but regular distributions in the population, like exponential distributions, the central limit theorem deals very well with that. So we don't have to worry too much about that, and you should always be checking your data for outliers anyways. You can't drop them willy-nilly, but you should typically rerun analyses with and without severe outliers. So remember, be careful about dropping outliers just cause. Some robust reasons to drop outliers, however, cases where you could drop them would be where you have a physically impossible datum. Remember that datum is the singular of data. So something like we saw before, people report that they work more hours in a week than exist in a week on the CPS. That obviously needs to go. Known social conventions make something unlikely. So some people also report that they work 20 hours a day, 7 hours a week. Technically not physically impossible, but actually probably is, but there's plenty of data on the CPS, for instance, on that same question that are not physically impossible, but just extremely unlikely given the social context. So you want to, consider at least rerunning the analysis with and without those variables included, observations. Okay, finally, what's kind of the meat of this lecture and the next one? The last assumption is that we somehow know sigma, the population standard deviation, but not mu, the population mean. This is clearly not a good assumption. Why would this be true? We would have a God's eye view on one feature of the true underlying population distribution, like the, say, standard deviation of wages, discussing wages or hours worked again, but we wouldn't know mu, the population mean, and we would somehow want to do inference on it. Why would that ever be the case? It's just not very clear. Now, there are reasons from biostatistics where these procedures were first developed where that might be plausible, but it turns out that there's a really simple solution to this. We just estimate sigma with S, so we just use S in all of our old formulae, and in the way I teach this, we've already been doing that. We just haven't corrected for the resulting and typically very small bias. The reason, and we'll talk more about this on Wednesday in my class or in the next lecture if you're watching this asynchronously, is that a sample with unknown sigma actually comes from a slightly non-normal family of what are known as T distributions, which converge on the normal very quickly as n increases, but our critical values are slightly larger for medium n's and much larger for small n's, like below, say, 50, just to use an example. And even then, really much below, like 30 is when you're going to start seeing huge differences. Let me make this point, though. This is what the asterisk here is in this case, which is how I write footnotes in these slides. This hardly makes a difference for most actual samples. So for the GSS, this makes virtually no difference. The really only reason to teach this, in my opinion, at this level is that we use T statistics even when they are no different to Z statistics, or T tests, I should say. The statistic actually is the same, but the probability that you get associated with it and the critical values are different. So the only reason to teach this at this level is that most software reports T's, because it does make sense for software to use the more applicable all-purpose kind of family of distributions, but for most actual cases, this makes absolutely no difference, so don't worry too much about it. And a concrete demonstration of that, consider the fact that we use the z-score of 1.96 as a critical value in constructing confidence intervals. Remember the fact that 1.96 is actually a bit of a rounding. It's the actual number is 1.959, blah, blah, blah. We can actually pull it up in Stata. Let me show you how to do that. Why am I opening Zoom? Stata. We'll say display inverse normal, and then we'll have 0.025, and you can see that it's negative 1.959964. Of course, this is trivial to round to negative 1.96 or positive 1.96. But note this really interesting fact that when we do that rounding error, we're technically making an error of like basically this magnitude right here, right? Or sorry, this magnitude right here. It turns out that if we just use 1.96, or let's say we actually like look up the correct t-value for a distribution under these circumstances, it turns out that it'll actually be between this and negative 1.96, meaning that the error from simply doing this little bit of rounding is often greater than the error of using a z in place of a t distribution later on. So it really doesn't make a huge difference. But I do think it's important just so that you understand like why every piece of statistical software reports this. So some general considerations before the next lecture, wherein I will discuss the theory of t-distributions at some length. First of all, note that statistical significance is not the same thing as practical significance. This is very often missed, and we haven't really called much attention to it yet. So for instance, any null, which is always chosen by the researcher, and oftentimes it's somewhat arbitrary, can result in statistically significant results. So you can pick any silly null and find evidence for an alternative. Your null doesn't have to be that some effect is 0. Your null could be that some effect is massive. And then it might just be obvious to everyone that it's not, like the gender wage gap isn't $2 million an hour, right? You can find results that say that that's not true. Of course you can. It doesn't really mean anything though. Like you have statistically significant evidence that some null that no one in their right mind cares about is false. Okay, who cares, right? But the problem is that when we confuse statistical and practical significance, and there's many subtler cases of this, then you get the problem of publishing sort of spurious results. So another point too, by the way, is that you don't even have to have a really arbitrary null. It can be a null that is sensible, but you have data that are just kind of marginally different to it. So let's make this a little bit more concrete. Let's say you have a null hypothesis, and again, I'm going to use nulls that are of greater interest. So we'll soon learn that you can find sampling distributions for differences in means. So suppose you have you're interested in testing the difference in means for women and men for wages, let's say. And you might have a null hypothesis that the difference is 0, and then you observe a difference in a particular sample, let's say a highly egalitarian place where there probably is not a very large gender wage gap. Let's just pick Sweden. So let's say your null hypothesis is that the true population difference in the mean wages for men and women, we would need to control for a whole bunch of other stuff, but there's ways to do that easily. Let's say, for people let's just pick a particular industry to control for most of that. So people working in, say, the teaching field, or people working, let's say construction. I don't want to be narcissistic. So let's say construction. So you have this null, and then let's say you find sample data indicating very clearly in a giant sample that men are paid about 10 cents more an hour, or krona, or whatever the relevant denomination would be. I should probably know if Sweden uses the euro or not. But anyways, let's say you find that, like equivalent of a 10-cent difference. Note that that's not hugely practically different. There could be all kinds of reasons that maybe we forgot to control for one factor, and that explains this pretty small gap. But the point is that in a small enough sample, you are going to fail to reject the null, and in a large enough sample, you will reject the null. And this is actually true generally. So any fixed null for a fixed raw difference becomes increasingly statistically significant as n increases. This is simple algebra. So if you just imagine the z-score formula, remember that root n is in the denominator of the denominator, so it's really in the numerator. And as you increase n, the test statistic gets larger. And you can have an arbitrarily small difference, but if it is from a giant sample, then it's probably a real difference. It's just a really small one, right? It's a one that's small enough that in, like say a common sample size, like let's say, sub-samples of 1,000 people each, which is pretty big, for a sample, may not be statistically significant. But if you were to observe the same difference with a sample of, 1,000,000 people or two sets of 1,000,000 people, it would turn out to be significant. Again, this is just another case of statistical significance not being the same thing as practical significance. It may well be the case that you simply, that's not politically salient in a particular place. Or again, it could be the case that that means, well, if we are, probably leaving out some relevant controls, once we include that control, especially if we think the control would mitigate the difference, maybe there really isn't much of a difference. It's hard to say. I'm just picking this as an example that is interesting, by the way. I have no comment whatsoever on whether or not this is true in Sweden. I'm just making the point. By the way, this also doesn't mean that statistical significance is meaningless or unimportant. It's actually super important, right? So if you're sure that you controlled for all the relevant variables, which you can do at higher levels, or you're just interested in knowing, I don't even care if we control for anything, just is there a gender wage gap? That is a politically salient question for sure, right? Do men, just generally speaking, make more money than women? Then you don't really care about controlling for anything. And then it could be hugely significant, depending on the context, that in a giant sample, there's very clear evidence that men make a little bit more an hour. That may be unimportant sometimes, it may be important sometimes. That's going to be contextually different, right? But the point is, and by the way, if that seems kind of fuddy-duddy to you, imagine or consider the fact that in many places, women have more education than men by a tiny amount. That's actually true in many parts of the US, for instance. So if you're thinking about that and you're well, women have historically had less social power, now they're leading by a tiny amount, it does matter for some purposes whether that tiny amount is probably noise in the sample or it's probably a real but small difference. It's just going to depend on the context whether or not the fact that there's very, very probably a small difference is meaningful or not. So that's the kind of point here. By the way, for the exact same reason, if you want a smaller margin of error, you should increase your n. That's pretty obvious. But generally speaking, small sample sizes or large sample sizes are better for a lot of things. Here's some more general considerations. Note that while confidence intervals may seem less arbitrary, they're almost always understood to be effective forms of hypothesis testing, and they exclude certain de facto null hypotheses. And they require us to select an arbitrary C, which is intimately connected to an arbitrary two-sided alpha. So even if we don't do a two-tailed test, even if we don't care about a two-tailed test, when we select a C, we are implicitly linking up with such a test. So it is ultimately just as arbitrary. Also beware of multiple comparisons. So as discussed in the last lecture, when you increase your number of tests, and technically speaking, all that means is as a class, for instance, when we do a whole bunch of population tests, or a test that the mean is or is not equal to a certain value, even if we are every single time, we are happening to select the exactly correct null, we should still expect about 5% of tests, if we're doing a two-tailed test in the conventional way, to have, say, false positives, right? False rejections of the null. We should expect, with a criterion of alpha equal to 10% of those tests, right? And so you can see that when you also flip through as an individual researcher and you're not even doing formal tests, you're just playing around with the data, you should expect, right, even if you are correctly guessing the exact value of the null hypothesis, that 10% of the time, at an alpha of 10%, you are going to just have enough sampling noise that you have a result that is different, even if you happen to know the true mu, right? That would be true. That's a way to think about it, is in rare cases where you happen to know mu, you have census data on it, you should still expect any sample you plan, there's a 10% chance that it's going to be outside of those boundaries just by coincidence, right? So you have to be aware of that. And as I note in the footnote here, this is actually a form of the birthday problem. So there's a really interesting, fun problem in introductory mathematical statistics where you have to figure out what's the probability of two people in a room who are gathered at random, assuming birthdays are kind of uniformly distributed, sharing a birthday. And that's not actually a terrible assumption. And it turns out to be surprisingly small, which is very similar to this problem here. So for instance, if you have 20 rejections of 20 nulls in your sample, you basically have like a 2/3 chance of getting one false positive or more, which is pretty high. So you want to be careful about that. Finally, I did want to discuss some optional Chapter 18 material on the power of tests. We don't really have a ton of time to go over this in my class, but I did want to mention some of these issues. Here is the first one of those. The power of a test, which is more relevant in planning a test, but is sometimes still useful to think about, is generally defined as 1 minus beta. And beta here is not a regression slope, but it's actually just defined to be the probability of failing to reject a false null. That's actually, pardon me, I made a typo here, a type 2 error. I just put these in like default order, 1 and then 2, but that's reversed. It's a type 2 error. And remember that alpha can be defined also as the probability, and we've just been saying this, of falsely rejecting a true null, or it's a type 1 error. So we've generally been concerned with this kind of more conservative type of error, or like what might be a more conservative approach, which is thinking about basically what's the probability that we're making like a kind of arrogant mistake. But we can also make mistakes that are not as arrogant but are still important, which is that we fail to notice something important as opposed to falsely say something important. Generally speaking, the power of a test is just defined to be basically 1 minus this probability of failing to say something important or reject a false null. So alpha and beta in this sense are almost the inverse. Don't confuse this with alpha and C being the complements of one another, but they're almost like the opposite sort of problem. Power is complicated because it's a function of our chosen alpha, the difference between the null mu naught and the true mu, and the standard error, which in turn is a function of the population standard deviation, and also sampling error, and the sample size. It's really complex. In practice, this is really only super important when people are planning their own samples. But I did want to show you a visual representation because it's actually quite nice to basically, kind of see how we can use the pictures of sampling distributions to visualize these things. So let's do that now. So here, we want to consider first this situation where we've got basically a sampling distribution under the null hypothesis and then the true sampling distribution. So what is beta? What is basically the probability of failing to reject a false null? Well, it's this purple area here. And why are we failing to reject a false null here? Well, basically under this kind of false null, which is here mu naught, and remember that the null basically is going to almost always be slightly false, like we're rarely going to exactly guess the null correctly. And often it's a straw person, so we don't even think it has a chance of being true. But under this circumstance, if this is mu naught here, we are failing to reject some null hypothesis at a given alpha equal to k, which would be this area here, because we have a really atypical sample given the true mean mu. So basically, we have a true mean mu, and we should be saying that we reject this, this is a really atypical sample given the true mean. But we've got this null hypothesis here, and we're not far enough away from the null hypothesis to reject the null. But we should be able to reject the null ideally in favor of an alternative that specifies that it's at least in this direction. Right? So if this is the true mean mu, we are hoping to be able to say something like, well, the true mean mu is probably larger than mu naught. But here we don't have a weird enough sample given our cutoff level of weirdness, given the distance between mu naught and mu, and given the spread in this sampling distribution here to be able to say that. So how could we basically reduce beta, or in other words, make the power of the test larger? Well, there's a couple of things. There's actually 3 that I want to focus on here. Basically, one thing we could do is reduce the stringency of the test, so we can make alpha larger, in other words, be more prone to reject the null. And here, that overlap then becomes much smaller. You can see that the alpha has increased, the rejection region has increased, meaning that we've made our test a little bit less stringent. We've increased the probability of making a type 1 error, or we've increased the probability of rejecting the null falsely when it is in fact true. But that doesn't increase the power of the test. Power, much like kind of, in this case, it's not really like true. It's power in like a very technical sense. It's the power of the test to, say something. It doesn't really mean the actual like desirable power, basically, at least not necessarily. There's ways to increase the power that are like fully grounded in good practice, and then there are some that are kind of spurious. This one's a little bit spurious because you can see that we're reducing this overlap. And again, remember that what's happening here is that in this case, we think that we're supposing that we could know that mu naught is false, and then we're saying like what kinds of sample statistics lead us to fail to reject the null in favor of the true known alternative. In this case, that's kind of would be a very rare situation. Here that overlap is smaller simply because we are more prone in this scenario to reject the null. So like for instance, coming straight down, this statistic here would be in this kind of arbitrary starting point, we would fail to reject the null, but here we would reject it, but that's only because we've made the rejection region larger. Another alternative, I want to actually come over here, is that we could also like move mu naught farther away from the true mean mu. What that really corresponds to in practice is selecting mu naught that is more arbitrary or is like more ridiculous. So we could, I gave the example before, say that the gender wage gap is $1 million an hour, then we can obviously reject it. The idea is that what we would be doing then, like let's say the gender wage gap, let's say we suppose that it's negative $300 an hour to women's favor, and then the true thing is that it's basically actually in men's favor positive $10 an hour or something like that. It's smaller than that, but let's say that that's what we're doing here. So then we could reduce this rejection, like this fail to reject region here, by simply sliding mu naught far away. So relative to this graph here, you can see that we've kind of shifted mu naught over, which means that now we'll have data where we can reject the null quite easily in favor of the alternative that the gender wage gap is higher, but that's only because we've set up mu naught to be something just pretty ridiculous, right? So this purple area where we have sample statistics where we can't reject the null in favor of an alternative is smaller, but that's only because we've made the null stupider. So that's not also the best strategy. A better strategy would be to simply make n larger, making the margin of error smaller, making these graphs, see here, we haven't shifted alpha, we haven't shifted mu naught, we've just made the graphs taller and skinnier because we've made the standard error smaller, and that has the effect of basically then retaining the original hypothesis, which we presume to be kind of like as extreme as one would possibly want it to be and no more, and to use a conventional and small alpha, but then to have smaller beta and thus a higher power. And we've been able to do that by simply making the sampling distributions more compressed. So that's a little bit about the power of tests using these pictures. I hope that helps.